Hello, I hope you're having a nice day. In today's video, I'll explain to you the Norton's theorem and how you can use it to simplify any circuit and thus obtaining the voltage or current of any resistor you like. Norton's theorem is very similar to Thevenin's theorem. The main difference is that in Norton's theorem, we will be working with current values instead of voltage values like we do in the Thevenin's theorem. Likewise, we have three steps in Norton's theorem that are exactly the same in Thevenin's theorem. But, as I mentioned already, we are working with currents. The first step will be finding the Norton's resistance. And to do this, we must first identify the resistor that we want to analyze. What do I mean by analyze? Well, the resistor where we want to know its voltage or current value. For this circuit and explanation, I'll say that we want to know the current and voltage of the resistor 1. In that case, we have to open the terminals of the resistor 1 to be able to do the first step, which is finding Norton resistance. So, we have to open the terminals of the resistor 1. So we obtain a circuit like this. As you can see, the resistor 1 is now open, so we can begin step 1, which is finding Norton resistance. When doing the first step, we must short circuit the voltage sources and open the terminals of the current sources, just like we would do in a superposition theorem. So our circuit as you can see, we got rid of the voltage and current source, so now we can actually find Norton's resistance. And how do we do that? Well, here we must analyze what resistor is actually affecting resistor 1. In the case of resistor 2, we can see that it won't have any effect on the circuit because this cable right here offers no resistance, so no current or voltage will flow through resistor 2, so we can get rid of it. Also, in the case of resistor 3, we can say that it won't have any effect on resistor 1, because you can see that due to the circuit being open here, no current and also no voltage will flow through it, so we can also get rid of it. So we're left only with resistor 4, which will have an effect on resistor 1, given that it's in the same mesh. So in that case, we can say that Norton resistance equals resistor 4. So that will equal 12 ohms. So we have completed the first step. Now moving on to the second step, we need to find Norton's current. And in the case of Norton's theorem, we can say that Norton's current is the current that flows through a short circuit between the two terminals of the resistor we are analyzing. So in that case, these two terminals will be short circuited, so it will look like this. And the current that flows through here is Norton's current. Now we only have to do some simple circuit analysis to find that value. In this case, I'll use superposition theorem to find it, because we have both a voltage and a current source. However, you are free to use whatever method you like, for example, nodal analysis or mesh analysis. But since I like superposition theorem a lot more, I'll use that. And superposition theorem establishes that a circuit with one or more voltage or current sources is equal to the sum of the simplified circuits when just one of these sources is being used. And what does this mean? In this case, it means that we'll build two circuits, one with the voltage source active and the other one with the current source active, and in each of these circuits we'll find the value of Norton's current. So, for the first circuit, we'll be analyzing it with just the current source active, so we can erase this and short circuit it. Why a short circuit? Well, because the superposition theorem establishes that when you are erasing, you could say erasing, or turning off the voltage source will be short circuited. So a cable will pass through it. In the case of the current source, its terminals will be open. So it's basically what we did when analyzing and finding the Norton resistance. So we can say that Norton's current will be equal to Norton's current 1 plus Norton's current 2. Norton's current 1 will be equal to the current that we obtain when just the current source is active, while the Norton's current 2 will be equal to the Norton's current we get when the voltage source is active. And why am I adding them? Why not just a subtraction? What's the science behind this, the reason behind the addition? Well, if you analyze the direction and flow of each current, you can see that the current and voltage of the voltage source will follow this direction, while the current of the current source will follow this direction. You can see that in case of the resistor 1, they have the same direction, so in that case, it will be an addition. If we had, for example, a current that went in this direction, so it had the opposite direction of the voltage source, in that case it will be a subtraction. We will subtract the Norton's current 2 from Norton's current 1. But as I told you, in this case it will be an addition. So now, let's find Norton's current 1. We must remember that current will follow the path of least resistance if there's a path where there's no resistance, where the resistance is 0. And we have such a path here. You can see that this cable offers no resistance. So in that case, no current will flow through this and this resistor because it will go in this way. So we can say that the circuit will be equal to this. And I think it's quite obvious the fact that Norton's current 1 will equal 2.3 amperes. So we can say that. And we already got our first value. It's that easy. Now let's analyze the circuit with just the voltage source active. As you can see, we open the terminals of the current source, as I told you. And because of that, no current and no voltage will flow through resistor 3, because this is open. So no current will flow through there, so we can get rid of the resistor. And we obtain the following circuit. It's also pretty evident the fact that the current in resistor 4 will equal Norton's current 2, because these two are in series. So we can say that Norton's current 2 equals resistor 4 current. So we just have to obtain this value. And how do we do that? Well, we can see that resistor 4 is in parallel to the voltage source, which provides 15 volts. In that case, we know that the voltage in resistor 4 equals 15 volts. So the current in resistor 4 will equal the voltage divided by the resistance. So we can say that the current in resistor 4 will equal 15 volts divided by 12 ohms. Why 12 ohms? Well, you can see here that the value for resistor 4 is 12 ohms. And this division will equal 1.25 amperes. Norton's current 2 will equal 1.25 amperes. And as I explained before, we'll have to add Norton's current 2 and Norton's current 1 to obtain the final Norton's current. Norton's current will equal 1.25 amperes plus 2.3 amperes. And this equals 3.55 amperes. So we now have finished the second and the hardest step in the procedure. We just have to do the final step, which is building the equivalent circuit where we'll be able to find resistor 1 current and voltage values. And this will be our equivalent circuit, where we have a current source of 3.55 amperes, which is the current that we just found, and two resistors in parallel. One resistor is the Norton's resistance we found, which were 12 ohms, while the 10 ohms resistor is resistor 1, the resistor that we originally wanted to analyze. So now we can find the current of resistor 1 using currents divider. So the current of resistor 1 will equal 3.55 multiplied by 12 divided by the total resistance, which is 12 plus 10. And this division will give us the final value for resistor 1's current. And if we wish to know also the voltage, it's pretty easy. We just multiply the resistance value, which in this case is 10 ohms, by the current. So the voltage in resistor 1 will equal 19.36 volts. It's that easy. Now if we simulate the circuit, we can see that the voltage is correct and thus the current is also correct.